So I posted the homework to turn in. Yeah. So I this morning, like I got up and I posted new problems. That'll be new next. I guess it'll be due the next Tuesday because it'll be like the entire next week as well. And then also the problems from these last 2 days that are going to be turned in tonight. Yeah. So you can find those, right? Okay. So let's talk a little bit about homomorphisms before we're going to spend some time doing some problems on homomorphisms. So we've already done isomorphisms, which is a good kind of jump start into homomorphisms. And so homomorphism is like an isomorphism, but you don't require it to be a bijection. So all that you need is that preservation of the operation. So like if you've got two groups, maybe G1, and let's be like really thorough here. Let's say the operation in G1 is star, and then you have G2, and the operation in G2 is pound or something. Then, and you have a map, phi from G1 to G2. This is a homomorphism if for all x, y in G1, we have phi of x star y is the same thing as phi of x pound phi of y. So just to be thorough, this over here is the operation happening in the group G1. So like the source group, if you will. And then this operation over here is happening in the target group G2. Like that. So, I mean, we've seen examples of this with high isomorphisms already. So this isn't like a huge new thing, but we just don't require bijectivity here. So like one example would be this map from, we could say Z to R, which goes n to 2 to the n, right? So we've got addition over here, and we've got multiplication over here, right? Then maybe if we called this something, maybe we'll call it psi. So notice if we have psi of m plus n, that's going to be equal to 2 to the m plus n by the definition of psi. But then that's going to be equal to 2 to the m times 2 to the n by, I don't know, like exponent rules or whatever. But then that's equal to psi of m times psi of n. So notice that we were able to take an addition and turn it into a multiplication. So that's what like a homomorphism is like essentially taking one sort of operation in one group and turning it into another sort of operation in another group. Okay, so I want to prove a result that I think maybe was sketched in the videos, but it's important enough to see more than once. Like you could maybe go back and read it too. It's that important that you should see it that many times. And then we'll look at an example and then we'll do some problems. Okay, so let's maybe call this a proposition. So let's suppose that G1 and G2 are groups, and I won't worry about the operation like star or pound or anything. I'll just write the two elements next to each other so it can be inferred. And phi from G1 to G2 is a homomorphism. Okay, so we've got, that's our setup. Then there are a lot of things that we get from here. Oh, I need one more thing. And H is a subgroup of, actually, I'll just put this in the hypotheses. So let's not worry about this. Okay. So we were going to prove these four things. So the first one is if H is a subgroup of G1, then phi of H is a subgroup of G2. So if you've got the image of a subgroup is a subgroup. That's what it's saying here. The images of a subgroup is a subgroup. So that's the first thing we'll prove. Then the second thing says this: if H is a normal subgroup of G1, so it satisfies that normality condition involving like cosets or whatever, then phi of H, so the image of H is a normal subgroup of phi of G1. So now this is really important. This is not necessarily all of G2. So just the image of G1. So you've got like some sort of picture like this over here. So you've got like your map over here, G1, sorry, your group over here, G1, your group over here, G2. Inside of G1, you've got a subgroup, which I'll call H, like that. And then remember, homomorphisms don't have to be bijective like isomorphisms do. So that means they don't have to be surjective. So this G1 might collapse to a little square in here, which is the image phi of G1. So in other words, everything outside of that square is missed. All right, there's no way to get to, say if we pick an element out here, there's no way to get to that from in here. And then this guy is going to be in here. So that's going to be phi of H. So what this is saying is that the image of H is a subgroup of the whole target group, but it's only a normal subgroup of the image. So that's what's going on here. Okay, and then we've got two more. And that has to do with if you have a subgroup on the right-hand side. So if K is a subgroup of G2, then phi inverse of K, really I should be saying the pre-image of K is a subgroup of G1. So that means if you've got a subgroup over here, you can pull it back to a subgroup over here. And then finally 4, if K is a normal subgroup of G2, then phi inverse of K, the pre-image of K, is a normal subgroup of G1. And I didn't make a mistake there. That's the entire group. So notice if you're doing a forward operation and you have a normal subgroup, you might lose something, but if you're doing this reverse operation, you will not lose anything. It's like kind of nicer in a sense. Okay, let's prove these 4 things. Okay. So we'll prove this by the subgroup test. You know, that's how we like to prove everything is a subgroup, right? So I mean, we've used the subgroup test like 100 times, so I won't like go into what that is exactly, but let's suppose that X and Y are in phi. Actually, let's maybe use different letters here. Let's say U and V are in phi of H. All right. And then recall, in order to satisfy the hypotheses of the subgroup test, what we need is this. U V inverse is in phi of H, right? That would finish off the subgroup test argument, correct? Yeah. Okay, so let's see how we can do this. Well, what's the entry fee into being in phi of H? So to be in the image, that means, so there exists X and Y in G1, no, sorry, in H, such that phi of X equals U and phi of Y equals V. So that's what it means to be in the image, right? It means that you're mapped onto by an element from that subgroup. Okay, sweet. Now we're like essentially just ready to make the calculation. So let's do it. So now we want to do U V inverse. So note that if we take U V inverse, that's going to be the same thing as phi of X, phi of Y inverse. All right, I just renamed U and V using the fact that they are inside of H, sorry, inside of phi of H. But now we can rewrite this as phi of X, phi of Y inverse. One of the things you guys watched was a property of homomorphisms, and one of the properties was that you can bring the inverse inside. Actually, I think we covered that when we did properties of isomorphisms a couple weeks ago. So you can bring the inverse inside, but now we know that we can smash those two together. So we're going to get that this is equal to phi of X, Y inverse. But we know that this is inside of phi of H. And how do we know that? That's because XY inverse is inside of H. Yeah. And how do we know that XY inverse is inside of H? That's because H itself is a subgroup. So H is a subgroup of G1. We did it. Okay, now it's a subgroup. Now let's show that it's a normal subgroup. So we're going to do that using the, I think the best way to do it is like with the element condition of the normal subgroup. So let's maybe recall that really quick. So N is normal in G if for all G and G, N and N, G and G inverse is in N, right? That's the element-wise definition of normality. Right? There's a bunch of definitions, but I think this is the easiest one to do like calculations with. It's kind of not as elegant to write down, but it's the easiest one to like check things with. Okay, so let's prove number 2 using this criteria of normality. So we want to suppose that, well, let's look at what we're trying to do. We're trying to show that phi of H is normal in phi of G1. So that means phi of H is playing the role of N over there, right? And phi of G1 is playing the role of our big G group. So when we pick our little elements, we have to consider them coming from those places. So let's do that. So let's suppose that little g is inside of, well, actually, no, I think this is fine, is inside of phi of G1, and little n is inside of phi of H. And again, just to reiterate what we want to show, so want to show is that G and G inverse is inside of phi of H. That would finish off showing that phi of H is normal, right? Okay, so let's see how we can do that. Well, we can use the fact that G and N are in those images, right? And what does it mean to be in the image of a sub? Well, really just a subset, but here we've got more structure, obviously. So then we have, maybe we'll call it X in G1, such that phi of X equals little g, right? So that's what it means for little g to be in phi of G1, and then a Y in H such that phi of Y is equal to n. That's what it means for n to be in phi of H. Now we're ready to make this calculation. So let's do it. So let's do G little n, G inverse. So let's notice that that's going to be equal to phi of X, phi of Y, phi of X inverse, just using our names for little g, little n, and so on and so forth, using the fact that they're in those images. But now we can smash all of this together. This is going to be phi of X, Y, X inverse. We know that that's because it's a homomorphism. That's like some of the properties of it being a homomorphism. But we know that this is in, let's see, what is it in? It's in phi of H because X, Y, X inverse is in H. And that follows because H is normal in G1, right? So look, X is an element from G1, Y is from H, X inverse is from G1. So we conjugated an element of H from an element from G1. We land back in H, that's because H is normal. So we did it. So that's all we need to do for number 2. Okay, good. So let's do these last 2. So these are often like, I remember as a student, at least, being a little bit afraid of this inverse image because I didn't exactly know how to work with it. But once you get used to the sort of the systematic like calculation type stuff that you have to do, it's really not super terrible. Okay, so let's see what we need to do here. We want to show that phi inverse of K is a subgroup of G. So we'll do that by the subgroup test again, right? So let's suppose that, I don't know what we want to call them. Maybe we'll call them like G and H. We're using all sorts of different letters here. So G and H are in phi inverse K. And what we want to show by the subgroup test is that GH inverse is also in the inverse image of K, right? That's what it would take. That's what it would take for this to be a subgroup by the subgroup test. So let's do it. What does it mean to be in the inverse image of K? Well, that means that if you apply phi, you land in K. So phi of G is in K and phi of H is in K, right? But then we know K is a subgroup, so phi of G times phi of H inverse is in K, right? By the subgroup test, you know, we were assuming K is a subgroup. But now we can smash that together, and this side becomes phi of G H inverse, which we know is also in K, because we haven't changed anything. These are the same. That's just using the properties of the homomorphism. Okay, but if you take something and when you map it, you land in the subgroup, that's exactly the definition of being in the inverse image. So GH inverse is in the inverse image of K. So this line right here is equivalent to this line right here. This is the definition of being in the inverse image. Okay. So we got one more. Now we need to prove the normality, right? So see, this is like almost, despite the fact you're working with the inverse image instead of the straightforward image, this is almost simpler because we didn't have to introduce new elements, right? Over here, we had to introduce new elements to make the calculation, but we don't over here. We just have to map over to where things are nice, do everything over there, and then like pull back. Okay, so let's do this. Last one. So we want to show that it's normal. Again, we're going to use the same kind of element-wise definition of normality. So, so 4, let's number this one as well. So let's suppose that, I don't know what we're going to call it. So we're trying to show that phi of k, phi inverse of k is normal in G. So let's say we've got G in G1, and we've got N in inverse k. And then just to reiterate what we're doing, by the, like I've said a couple times already, by the element-wise definition of normality, what we want to show is that G in G inverse is in P inverse K. That's what it would take. Okay. But now we're going to use the same sort of strategy that we did over here. We're just going to map with phi to land back in the group that we know about. So we know that in the G2 group, everything is normal. So let's map over there. So let's look at phi of G, and then phi of N, and then phi of G inverse. So let's just point out where all of these things are coming from real quick. So this thing is coming from G2. It's actually coming from like phi of G1, but that kind of doesn't matter so much. It's coming from G2, so that's good. That means this thing is also coming from G2, right? Because those are just arbitrary elements in the domain, so those get sent to just some person in the codomain, right? And then this phi of N is in K, and that's because of this property right here. If N is in the preimage, then phi of N is in the thing that you're taking the preimage of. Okay, but our assumption, which was erased, is that K is normal, right? So since our assumption is that K is normal, that tells us that if we do this kind of action with a normal subgroup, we land back into that normal subgroup. So let's see, this is because K is normal in G2. But now we're home free. Now we can smash these together using the properties of isomorphism, or homomorphism, I should say. So this is going to be phi of G in G inverse, but we know that that's in K. Here we just, like I said, use the properties of homomorphism to those two are equal. So since the top one's in K, the bottom one's in K. But now phi of this being in K is exactly what it takes for the inside to be in the preimage. So that means G in G inverse is in phi inverse K, or preimage K under the action of phi. Okay, sweet. So now, okay, so between this and the stuff that you guys watched, I think we're ready to try a couple homework problems, and then we'll like jump back and do some other examples. I have a couple of other examples that aren't homework problems, but I want you guys to try one or two on your own for 10 minutes or so, just to get the problem solving juices flowing. So I assigned them, they're on the moods, is what everyone calls it. So let's see, I've been logged out, so it's What? Week 11, 12. So 1, 2, 3, 4, 5, 7, chapter 11. Is that right? Chapter 11?
Mm-hmm.
Yeah, that's right. Chapter 11. So you guys maybe try number 1. It's a good review of linear algebra. And then we will kind of tag team 2 since it's a multi-part question. So I'll do one, you'll do one, I'll do one, you'll do one. And then we'll have a lot of good experience by the end of the class. And then we'll probably do one of these other examples that I have cooked up. So that's the sequence of events for the next 10 minutes. Does that sound good?
Yeah.
Great.
Oh, wow. Did you finish your internship application?
Yes.
Like the big Google one?
Yes.
Yeah, I did that yesterday or the day before. Sorry, I did that the day before. So that's sweet. I was so pressed all the time. How are you, Caleb? Pretty good.
But the line is along at the health center. But the line is along at the
I mean,
health
she
center.
said you can cut in front of people since you got taller than me.
Yeah. Okay, go get tested today.
No, it's not long enough over there.
Oh, isn't it?
You just walk up, call them. maybe.
I remember Brandon told us to never go down there because it's always
Full.
full.
It's never full.
Seven.
Nobody's ever there.
Do the whole wire.
Exactly. Skip class to do live streams.
Yeah, that got
Going-
funny. That got
going
funny.
with
Oh my gosh, I hate teachers who are stupid as fuck. Don't read their emails and then cause me problems. At Rainbow Spear.
Yeah, I don't know who that is. I'm sorry you're struggling with that though. Things can be frustrating. I forgot to edit the YouTube portion of the podcast, but like the audio portions is all good though. Can you believe that we did like 14 episodes? I'm sorry, I wasn't over than that.
Okay, so let's look at this first one real quick. So it is the map from GL2 to R that takes determinant to, well, it takes something to the determinant. So like maybe we could write this like a little bit more carefully like this. We've got determinant is a map from GL2R. So remember that's 2 by 2 matrices with real entries whose determinant is non-zero, right? So then this is going up to R times. So that's non-zero real numbers. Operation is multiplication. So we want to show that that is a homomorphism. So what we want is that the determinant of AB is equal to the determinant of A times the determinant of B. So this is like a formula that should be somewhat familiar from linear algebra, like the determinant is a multiplicative formula. You can prove it in general for an n by n matrix, but to prove it for a 2 by 2 matrix, I think the best way to do it is just like by doing a sufficiently general enough like example calculation. So let's do that. So let's set A equal to the 2 by 2 matrix A, B, C, D, and then we'll set B equal to the 2 by 2 matrix. I'm going to call it X, Y, Z, W. You could do anything you want, really. Okay. And now essentially what we want to do is calculate the right and left-hand side of our goal equation and make sure that they're the same. So before we get started, maybe we'll calculate AB. Let's notice that AB is going to be AX plus BZ. So that's the first entry, right? We did that. And then it's going to be AY plus BW, CX plus DZ, cy plus dw. So there's AB. Right, and now, like I said, let's calculate both sides. So the determinant of AB is going to be AX plus BZ times CY plus DW minus AY plus BW times CX plus DZ. Right? Just the standard determinant formula. This times this minus that times that. Okay, and then determinant of A times determinant of B. Well, here we'll use like the standard determinant formula for each one separately. So that's going to be AD minus BC. That's the determinant of A times XW minus YZ. Yeah, and then, I mean, what do you do from here? I mean, essentially, you just multiply this out and show that it's the same as what you get when you multiply that out. So just multiply both out and compare. That's all you have to do. It's just like pushing symbols around. So I'm not gonna do that. So multiply out and compare. Yeah. I mean, you can see that there's like a bunch more terms up here, right? So there's going to be some stuff that cancels. Right. And then you have like less terms down here. So like whatever doesn't cancel is what you're going to have down there. Okay, cool. So now let's maybe recall this notion of kernel real quick. So one of the videos you guys watched was about the kernel. So that's like a super important normal subgroup of the target group. So if you got phi from G1 to G2, you define this thing called the kernel of phi. So that's going to be all G in G1, where phi of G is equal to the identity. The kernel. And in the video, it was proven that this is a normal subgroup of G1. That actually follows from a result that we just proved, because notice that it is exactly the pre-image of just the single element E, but the single element E is a normal subgroup. So it's a pre-image of a normal subgroup. That makes it a normal subgroup. That's really all there is to it. But whenever, like we talked about on Tuesday, like we talked about on Tuesday, if you're talking about a normal subgroup, the next word out of your mouth should be, what's the quotient group? We're not going to talk about that today. That's what we'll do next week, is what happens when you take the quotient group with the kernel. Important stuff happens. It's really important. But, you know, knowing that that's normal pushes us towards that direction. Okay, so let's find the kernel of the determinant. So notice the kernel of the determinant map, like this over here. Well, that's going to be equal to, let's just do it by the definition. So that's going to be all matrices A in GL2R such that the determinant of A is equal to the multiplicative identity over here. But the multiplicative identity is just the number 1, right? So we wanted to expand this out. This would be like A, B, C, D, such that AD minus BC is equal to 1, right? That's all you can do to show that. That's all you can do to like describe the determinant. There's a name for this. This is actually a name. This is called SL2, the special linear group, for what it's worth. It doesn't really matter so much what it's worth. Okay, let's do one more example and then we'll go through and have you guys try some. So let's think about this group. So let's let G be, I'm going to use some notation here. This is R adjoin X. So this is all polynomials. And then the operation is addition. So just polynomial, you're just adding polynomials together. So, I mean, clearly there's an identity, it's just 0, the constant polynomial 0, and then you can find inverses, because if you take minus a polynomial, it's still a polynomial. And then what I want to do is define this map phi from G to itself like this. So phi of f of x is going to be equal to the integral from 0 to x of f of t dt. And now let's check that that's a homomorphism. Well, actually, let's do an example. Check that it's a homomorphism, and then describe the kernel. Okay, so do an example calculation. So let's take f of x equal to 3x squared minus 9x plus 1. That's a polynomial, right? So now let's calculate phi of f of x. So that's going to be the integral from 0 to x of 3t squared minus 9t plus 1. And now we just do the end of calculus 1 on this, right? So this is going to be equal to, what is it? T cubed minus 9/2 t squared plus t evaluated from 0 up to x. So I just took the antiderivative. But now plugging in x, I get x cubed minus 9/2 x squared plus x. Plugging in 0, I just get 0. So that's the kind of calculation that we're talking about here. So now let's check that it's a homomorphism. So let's take f of x and g of x in this thing that we're calling our group G, which is just polynomials. So those are just polynomials. And let's calculate phi of f of x plus g of x. Remember, our operation is addition, right? If the operation was multiplication, we'd actually be a little hosed. It wouldn't be a homomorphism, like, because the antiderivative is like a little bit trickier with multiplication. Okay, so this is going to be the integral from 0 to x of f of t plus g of t dt. But then we know from calculus that the integral is an additive thing, right? So we can rip the integral apart. This is going to be equal to the integral from 0 to x of f of t dt plus the integral from 0 to x of g of t dt. Right? There's the additive rule for integration. But now that's just phi of f of x plus phi of g of x by our definition of f and g. So note, look what we did. Phi is going from G to G, so that means addition is the operation of both sides, right? Which is good. Addition is the operation of both sides, and that's exactly what happened. This thing like factored across the operation properly, right? Okay, so let's look at the kernel. So kernel phi equals, so this is going to be all f of x and g such that phi of f of x equals the additive identity, which is 0, right? So we just got to keep in mind what the identity is. So for the arbitrary definition, we'd write E for the identity. In this case, we knew the identity was 1 because we had multiplication. Here, the identity is 0 because we have addition. Okay, cool. So now, well, let's see what that really means. So in other words, we have the integral from 0 to forgot what my brain rebooted right there. I don't like, totally lost my train of thought. Of f of t dt equals 0, right? That's phi of x, phi of f, right? So we want that to be equal to 0. Okay, so, and this has got to be true for all x. So, well, what kind of polynomials will have that happen? I think they're just constant polynomials, right? I mean, think about it. Let's say f of x equals a0 plus a1 plus a1x plus an x to the n, right? And what we want is the integral from 0 to x of a0 plus a1t plus up to an t to the n to equal dt to equal 0, right? That's phi of x. But now just doing like term by term anti-differentiation, this is going to be a0x, right? Plus a1x plus a2 over 2x squared. Sorry, this should be, this should be a1 over 2x squared because we took the antiderivative, all the way up to an over n plus 1 x to the n plus 1. So that's the antiderivative, right? But we want that to be equal to 0. But notice if that is equal to 0, then all of these are equal to 0, right? Yeah, I mean, if we've got a polynomial, right? We took the antiderivative of a polynomial, we got a polynomial. If that polynomial is 0, and this is 0 for all x, then that means all of the coefficients have to be 0. So we have a0 equals a1 equals up to an equals 0. But what does that mean? That means that our original polynomial was 0. Right? So the only way to get into the kernel was to be 0 in the first place. That's the only way to be inside of the kernel at all, is to be 0 in the first place. Otherwise, you get mapped to something that's non-zero. Okay. Oh, and I want to point out that in this very special example, this is actually also a linear transformation. And this could be, you know, if we took some of the words out of it and changed some of the words, this could be a nice linear algebra problem. Instead of kernel, we might use like null space or something. Okay, cool. So let's look at this next problem from the homework. There's like a A, B, C, D, E. And we'll just tag team them. So maybe you guys will try A, and then we'll go through B together, and then C, and then D together, and then so on and so forth. All right, let's talk about this first one and then we'll talk about the second one at the same time. So let's make sure my framing is good. Okay, so this first one is a map from multiplicative real numbers into GL2. So we've got this map phi. Like I said, it goes from multiplicative R numbers to GL2R. So those are invertible 2x2 matrices. And it does this. It takes A and sends it to 1, 0, 0, A. All right. So we first want to show that it's a homomorphism. Homomorphism. So that means we need to look at phi of AB versus phi of A times phi of B. But the calculation here is pretty simple. So we won't like calculate both sides on their own and then like do a bunch of stuff to show that they're the same. We'll see that they're the same like pretty quickly. So notice that that is going to be equal to 1, 0, 0, AB, right? By, oh, Siri, I don't need anything. No, I don't need you. Okay, and then, well, we know a little bit about matrix multiplication, especially if the matrices are diagonal. It's like pretty simple. So since these matrices are diagonal, we can factor them just the way that we would like to. So notice that this guy will factor like this, right? And just by matrix multiplication, those two are the same. But now this thing is phi of A times phi of B. So it is a homomorphism. And then it says describe the kernel. So let's see, A is in the kernel of phi if phi of A is equal to the identity matrix. So that's 1, 0, 0, 1, right? But if phi of A is equal to the identity matrix, well, phi of A is 1, 0, 0, A. So that means that A is equal to 1, right? In other words, that means that the kernel of phi is just only the singleton 1. That's all you get. That's the only way to get a 1 right there is to send a 1 there. Okay. So now let's look through question B, and then we'll let you guys look at question C. Okay, so let's look at B. It's the same sort of setup in that we take phi from multiplicative real numbers to 2x2 matrices. But now the operation is slightly different, right? We've got this off diagonal type of entry. Oh, yeah, good point. Thanks so much. Great, thank you. So it's an additive group of real numbers to GL2. And what happens is that we send A to 1A, 0, 1. And now let's see what we get on both sides. So notice that phi of A plus B is going to be 1, 0, A plus B, 1, right? And then let's see, phi of A, phi of B will be 1, 1, 0, A1, and then 1, 0, B1. But then if we multiply those, what do we get? We get 1 here, get a 0 here, and then we get A plus B here. Right? So it is a homomorphism. So we're good again, right? Now, let's see what's the kernel. then we'll do the same kind of thing that we did over here. A is in the kernel of phi if and only if phi of A is equal to 1, 0, 0, 1. But that's if and only if A is equal to 0 in this case, right? Because now we need that entry to be a 0. Okay, but that tells us if the only way to be in the kernel is to be 0, that tells us that the kernel is just the singleton of 0. Okay, so let's maybe take a couple minutes and look at C. And then maybe C and E. Not D, because that's actually one we just did. So. Okay, so real quick, you guys will not be in proof class today. And over the last 2 days, one person has come remotely one of the days. So I'm gonna email everyone and just say that, like, if you want me to meet with you, email me. That seems good, right?
Yeah.
I don't need to sit in that room with the Zoom on with no one there.
I mean, we could be there, we should be standing in line. on a Zoom call.
Sick.
Yeah. I don't even have a Zoom on my phone.
I mean, you could get Zoom on your phone. Okay, so that's the plan. That doesn't really matter so much for you guys, but I'll send an email out to everyone regarding that. The stuff that we're going to cover today is pretty straightforward, right?
Yeah.
It's hard for you guys because like we've been doing that in this class, right?
Mhm.
Yeah, anyway, so that'll be the situation. If anyone wants to meet with me, they can. Yeah. And do some preemptive. Okay. So like this afternoon, do some preemptive sleep. They're getting their second dose.
So basically saying that.
Yeah.
So what's that really mean for class?
What?
What's that really mean for the proof class?
Well, no one's been coming remotely for the past several days. So, and then the 2 in-person people are getting their second dose of their vaccine today, so they won't be in class. So I was just gonna have like, you guys email me if you wanted to talk to me during that class. So look over the material and see if you want to talk to me.
Okay, we'll do that. Okay,
Great. Thank you. Okay, let's look at this abstract algebra problem. I'm wearing the headphone, even though it's coming from there. I'm like, I don't know what it's pointless. I thought that I had the sound coming from here again, whatever.
You might not wanna fix your phone.
No, I don't know. Okay, where's, I mean, I only have 37 tabs open. I don't understand why I can't find this one immediately. Okay, so this is called the trace. The sum of the diagonal elements. And this is actually like oddly, the trace is a pretty important function that you can do to a matrix. The trace tells you a lot. In fact, the trace of a matrix is equal to the sum of the eigenvalues. That's cool. And the trace of a matrix is the same regardless of what coordinate system you're in. So like similar matrices have equal traces. This is like just kind of some aside linear algebra stuff, which is interesting to know. We're kind of built on the back of this question because, you know, I know that sometimes you look at these and you look at, well, what's the big deal about this function? Well, this is the trace function. And there is some important stuff about this trace function. So we've got phi again goes from GL to R, but now it goes to additive real numbers, right? And it takes a 2x2 matrix A, B, C, D. Like I said, it sends it to its trace, which is A plus D. So let's see if this is a homomorphism. So let's say, well, let's maybe write it like this. A is sent to trace A. So now let's say A is equal to A, B, C, D. And let's say B is equal to X, Y, Z, W. Like that. But that means that A times B is equal to AX plus BZ, AY plus B. Well, we did this calculation before, right? Multiplying matrices. CX plus DZ. And then finally CY plus DW, like that. Now let's compare. So phi of AB, so that's going to be the trace of AB, which is just this plus this, right? So that's AX plus BZ plus CY plus DW. Then let's look at this. Let's look at phi of A plus phi of b. So that's going to be the trace of a plus the trace of b. Keep in mind that we are in additive real numbers here, right? We're in additive real numbers. That's going to give us a plus d plus x plus w. Those are not the same, right? Yeah. Not the same. Now, let's see. Yeah, those aren't, anyway, those aren't the same. There's actually an algebraic structure called a Lie algebra where the trace is a homomorphism, but you have to have a different operation. It's not just matrix multiplication. It's like if you, I won't talk about it too much. There is some place where that's kind of more well behaved. Okay, now let's look at E. Okay, E is this, essentially it's a projection map. So you probably saw something like linear algebra. It was just like wrapped up completely differently. So if you were to take this matrix and instead write it as a 4 vector, then this kind of projection map would be pretty common in linear algebra. But, you know, like if you're looking at additive group of matrices, then that's like essentially it's the same thing as the additive group of like 4 vectors. You're just arranging the numbers differently, but it's the same. So here we've got phi from M to R to R. And this is additive 2 by 2 matrices, additive real numbers. And we've got phi of A, B, C, D just goes to B. So we're just projecting it to B. It's like we're shining a light on top of B and we're getting the shadow of B, but nothing else, right? So this is a homomorphism, right? It's pretty clearly a homomorphism. Notice if we take phi of A, B, C, D plus X, Y, Z, W, that's going to be equal to phi of A plus X, B plus Y, C plus Z, D plus W, but that's going to be equal to B plus Y, right? But then that's going to be equal to phi of phi of A, B, C, D plus phi of X, Y, Z, W. So it is a homomorphism. Now you might ask what the kernel is. Well, we need to know what the identity is over here, and that's going to be 0, right? So that means the kernel is going to be every matrix that's sent to just the number 0. But that means that A, C, and D are free to be anything you want, right? They can be anything you want as long as B is 0, because that's all we see over here. So this is going to be everything of the form A0, C, D, where A, C, and D are real numbers. So you've got this like 3-dimensional kernel. Like that. Right. 1, 2, 3. Got 3 choices. There are infinitely many things in your kernel, which is fine. Okay, cool. Okay, so good. I think we've like warmed up into homomorphisms enough, a lot. And now we're going to look at, well, what is really great about homomorphisms? And those are these things called the isomorphism theorems. And that'll be the stuff that you guys prepare for next week. And we're going to do a bunch of examples next week. I'm probably going to also post this optional video that I made where I did like a full hour of isomorphism theorem examples. I like really suggest you guys look at that. Maybe I'll like assign it, but make it skippable so that you can like skip around. So you don't have to spend the whole hour if you don't want to, but I think it provides a lot of really good examples, and we'll expand on those examples in class as well. So that's the sequence of events. We got the homework due tonight, right?
Right.
Hopefully you guys are done,
Oh,
It
yeah.
is. I was gonna say.
because you're gonna be down.
I actually have his home for Thursday.
And then we'll, and then some new problems are up. That will be due, not next Tuesday, but the Tuesday after. Okay. So that's what's happening. Is that cool?
Yeah.
Great. Have a good weekend, everyone.
Yeah.
I'm gonna power my work in Friday's class.
You know, like, you'll probably be fine. I'm kind of a baby. To be honest, like, I think I said this last time, right?
Yeah.
I'm like affected by this stuff. Essentially, everyone else I know, my dad was like down for the count, but he's 80 years old. So I have the constitution of an 80-year-old, so.
Yeah, my mom told me she's taking more than chocolate on Gatorade and water.
Yeah.
Yeah, I'm home now. And but like my dad was on the taxes. I mean, he had his thoughts in January.
Did you guys see this news article that says wiping things down doesn't do anything?
Yeah, that's all I'm doing. I'm kidding. I mean, it helps some, well, this is a mix of it.
Oh, did you like the Apple event?
I did. Yeah. I